So this is my wood stove water here, put together with a stainless steel coil in the firebox here. Cold water comes in the bottom there and proceeds to come up and out, stainless steel, and then I embedded the fire brick around it so it was flush and wouldn't get knocked around when you put wood inside. And just had to cut the steel a little bit with an angle grinder in there. You can see the corner and the top shelf cut off, and it fit in there really nice. That goes around back here, so you've got your cold in the bottom and then your hot coming out. This here is air intake for combustion. This house is really tight, so I needed air intake for combustion, and that is adjustable by a blast gate for a vacuum system here. So this is open. This is all as much oxygen as it can take, and then it's like choke. So after you get it going, you can stoke it down. And that has an air intake that goes around the foundation when I built the house. So that's preheated to 55 degrees, that air that comes in underneath there from a 4.5-inch pipe. And so that helps when it goes into the firebox, because it's not coming at like 0 degrees or whatever the ambient air temperature is outside, and cool the box. So that helps as far as bringing in fresh oxygen, and then also oxygen that's, air that's tempered, combustion air that's tempered. And those two fans, of course, will kick on. Those are Peltier devices that will turn the thermal energy into electrical energy and turn those fans and help cool that blade, because that's a single wall. And then it goes to like a double, and then an insulated stainless steel double, or some people call it triple wall, going all the way up and out. This is a copper tank I found from a house years ago. Basically, the house is getting sold, and I was able to kind of barter this for him for some of the work of getting it out and doing some other plumbing for him. So I got that tank, which is great, and I polished it up and it looks awesome. So that's a rated 250 PSI. I think it was made in the 30s. Turns out this company made their water tanks so well that they never went, they lasted really a long time, and they never had to be replaced. I can show you here. It's I think it's Traeger Traeger, 40 gallons and rated to 150 PSI, and then it says test 350 PSI. Wow. So it's 40 gallons, 350 PSI capacity, and then I have a pressure relief valve here, and then another one up here, which is also an air outlet valve. So that's 150 PSI pressure relief, and then lets the air out. So as this thermo siphons through and heats up, if no one's using the water in the house, I have the hot out going to another water heater holding tank in here. So that comes in here and comes in the cold intake, and there's a check valve on this line so it won't go back into the cold line, and then it will then circulate up through this check valve, which is a one-way valve, and go back to the cold return, back to that copper tank. So that will allow the thermosiphon to circulate when the hot water is not being used. And then that will allow kind of it to create a larger thermosiphon circuit and bring that hot water back into the cold intake, and then complete the loop. And then when you use the water, of course, it will drain the water. It will bring cold in here and then push this hot water out through that line, and then push that hot water to the faucet or the shower. But one thing I'm going to have to put on is an anti-scald. So a lot of people say you should have a pressure relief valve right here. I'm probably going to plumb one in here. I knew if I had one up here and another one here, both rated at 150 PSI, I think 210 degrees Fahrenheit, something like that, that I should be okay, because this is at the highest point, and then there's another one there. So if this system's a pressurized, that's going to be the same pressure as that. Temperature might be a little bit different, because I guess you could have some cooling in here, but essentially this is the ambient temperature you're looking to measure when you're using these pressure relief valves. For pipe insulation, I just use those pool noodles from the dollar store that have a 3/4 inch diameter, inner diameter, and they work great because they're a lot cheaper and they're thicker, and you can just get red and blue, or if you want to insulate your cold lines. I do not, I just insulate my hot. So anyway, this will make plenty of hot water in the winter when we're running this, especially when you get good hot coals inside the fire brick in there. That will just auto thermosiphon within this tank, and then as that heats up, that will push that warm water into the colder water through those series of check valves, keeping it from backflowing. Yeah, if anyone has any ideas for any improvements, or hopefully this helps give other people ideas. I know one thing I'm going to do is probably add a drain right here, cut this and put a drain valve. There is a drain on the bottom of this tank that I can access through this board here. So it's actually a lower point than, well, yeah, than there, because this would only drain to at that level. So there's a bone plug under there, and I can do that and drain the tank from there. But anyway, so yeah, so fresh air intake, and then the coil, all can be done with, I did it with basically I used a carbide bit for this to cut the 4-inch hole in here, and then this stainless steel kit came with a bit, and I bought that on eBay. I think it was about $160 for that coil, with the drill kit and a pressure relief valve and instructions of how to do it. But I guess this is the most efficient way. Some people wrap copper around the neck here, and I was gonna do that, but I like this clean look better, and I didn't want to go through the trouble of trying to wrap soft 3/4 inch copper around 6-inch pipe. It can be very difficult, and I wanted to try to make a nice clean fitting, so it's getting there. It's there's a few more improvements I have coming for it, but other than that, I will give you an update when we use it in the winter, and see how well it does. I'm thinking about putting a temperature sensor and a flow meter on there, and maybe doing an Arduino project, something like that, and logging the temperatures and then how much water we're using, and then that's going to be able to give me some ideas of cost savings compared to using LP gas from the on-demand heater. And then I did have an option over by the on-demand heater, because that other water heater in here, this video is getting kind of long, but this other water heater is actually powered by, has 2 DC elements that act as dump loads or bypass loads for the windmill, which is what this controls. This controls the windmill, and when the batteries are full, when this 48-volt battery bank in here is full, that will then send the electricity from the windmill into these elements and heat this water. But it's never going to get hot enough or hotter than the wood stove. And so, and also in the winter, we're going to have less sunlight from the solar panels charging this battery bank. So we're going to depend more on the windmill, and that's going to mean less dump load going to that, and then more dependency on the wood stove in the room next door. So we'll do a different video on the battery bank and how that works. I just have these weights on here to keep the boards down because they're a little bit bowed when I made the battery box here. And I'll make a different video on this system that I'm working on, which is working pretty well right now. Anyway, so that's the wood stove water heater. Hope you guys enjoyed. Take care.